Okay, so let me try to get this to work. Oh yeah, thanks. The slide's already up. Um, huh, okay, this is still working. Yeah, good. So I want to talk about neutron production in extensive air showers, and I know that this has not been considered for quite some time. And we worked on it, and I will show you why. If you want to read the details, there's a paper that is recently posted to the archive, and well, we will hope that it's going to appear very soon. And this is the group of people who have worked on it, and you will see. Okay, let me start with something very basic, and the point is here. Already Lindsley reported with the Volcano Ranch with fairly thick plastic scintillators that he sees very nice air shower signals, but he also sees particles coming very late. What means late? Late is like 10 microseconds, and those people who know a little bit about air shower physics, you might have a trace that is 4 microseconds long or 3, but 10 is very unusual. Well, because the shower front isn't really so thick. And that is, of course, in the early days. This, you see, this is, by the way, the reference clock here that they had, and this is all photographed from an oscilloscope. And so a number of people thought about it, and Greisen came up with the idea that neutrons actually in air showers because they can move very slowly through the atmosphere and don't get stopped because they aren't charged. And then later, Watson gave us actually a note typed by Michael Hillas. And in this note, it's basically saying already most of the physics. It's that the late passes are most likely neutrons, that they are not very much stopped, and they come like a cloud later. And the water Cherenkov detectors, you don't expect to see much of those. Okay, and of course, there's since then an extensive literature on it. And for example, this is a recent paper that appeared here this year. And you see 2023 August. And it shows, for example, the number of neutrons relative to the size of air showers in the Tian-Shan measurement here. And just to give you an idea, this is fluence per square centimeter. So this is like 200 neutrons per square centimeter for an air shower that is a little bit above the knee. So it's not a small number of neutrons that are coming there. And so why is it actually interesting? First of all, it's a component that is, you will see that we can nowadays measure much routinely better than before. But there's also another point, and I want to explain this a little bit here as a motivation. Let's assume you have an air shower signal you see in the scintillator, and I just drew a very simple one. And the neutron is going to come very late. So how would you typically work? You have a capacitor you charge with the signal, and this is how the voltage goes up of the capacitor. And then once it's charged through a resistor, it's of course going to be drained and voltage goes down. Now, depending on the experiment, like Agasa measured the time actually for discharge. This is like a logarithmic amplifier. Other people measure the voltage after a certain time, but you do it typically very late after this pulse because you want to get the integral of the entire pulse. If there is a neutron coming very late, even if it had only less than 10% of the signal, so it would be negligible in the first hand, but if it's putting charge on the capacitor very late, you're actually wrong by a factor of 2 with the signal. So it's a big effect. And so it could potentially, depending on how you measure, it could spoil your measurement and you wouldn't see it because if your electronics doesn't show the trace, you don't see it. Okay, now we have modern experiments with traces, and this is, for example, the upgrade of the Auger observatory where you have the scintillators on top of the water Cherenkov. The blue line is a measured event in the water Cherenkov, one particular station, and the red histogram is what you see in the scintillators. And you see indeed late coming particles that are not present anywhere else. And you actually see this routinely, and this is what David Schmidt showed already in the ICRC 2021, where this plot comes from. Now you could ask, okay, telescope array has scintillators, so telescope array should have it. And so I looked at the Amaterasu event because we saw very nice traces there, and you have 2 layers in telescope array, 2 scintillators on top of each other. Now, neutrons typically would interact in one only, or get elastically scattered. They can do in both. But we do see features that might actually be compatible with late coming neutrons. And so we do have access to it. And I would be very keen to see the IceCube data, IceTop, because IceTop should also see it. Okay, now if you want to simulate this with the latest state of the art, because we have learned a lot over the years, you typically go to Fluka because Fluka has the most sophisticated hadronic interaction model for neutrons. And if you go to low energy neutrons, you have to distinguish really low energy, that's 20 MeV and below, so it's really low, and a little bit higher energy. And Fluka has like a matrix formalism because it's just too many neutrons, you can't follow them, so you multiply propagation matrices for the 20 MeV and below, and for above you do Monte Carlo. And then there are special things like neutrons in air, like nitrogen, oxygen. The green is nitrogen, the blue is oxygen. Neutrons have cross sections that are vastly different depending on the target. And there are resonances, there are all sorts of weird features you have to take care of. And so it's actually, this is tabulated things. This is what people have measured at nuclear reactors at other places and whatever. Yeah. And it's needed, of course, for shielding purposes. And that's built in Fluka. And one of the important things is neutrons lose energy by elastically scattering. So the most efficient target is essentially hydrogen, because if you have a neutron coming in, a hydrogen, same mass, it's like you share the energy. And so this way you produce actually thermal neutrons, and the heavier the target is, the less energy the neutron loses. Now you can do a benchmark with Fluka and you calculate the inclusive flux of neutrons from cosmic rays at different heights. This is a flight here actually with the airplane. This is a Concorde flight. You go all the way in the grammage from 200 to 50 grams, and you see the neutrons, and they go all the way from high energy to 10 to the minus 8 MeV, thermal neutrons. So they are just very slow. And this is in the airplane, so there isn't much target to scatter. If you do it in a different environment, you actually see the backscattered neutrons from the ground. And so you can do, if you look at the neutron energy spectra, depending on what you use this is for example sand. If you just use air, you're wrong. So it's really important to get all the nitty-gritty details right if you want to compare to data for neutrons, because the environment matters a lot, because neutrons is like a cloud. They move just everywhere and they feel everything, and they get backscattered from the soil. And okay, so what do we expect for air showers in principle? The easiest way is to compare things with muons. And for muons, we know how this works. The number of muon scales with the primary energy to the power beta. Beta is maybe 0.9 or a little bit more. And you have superposition models, so it's 40% more muons for, let's say, iron showers. And we know this is what it looks like. In the case of neutrons, it's really different, because you first of all have neutron, anti-neutron, or proton, whatever, antiproton or lambdas or whatever production, pair production of baryons that in the end produce neutrons. But you also have a very dominant channel, and that's the disintegration of the target nuclei in air. So oxygen, nitrogen disintegration will produce neutrons. And that's produced by photons. So that's scaling with the photon number in the air shower. And it's completely different from this one. Then, of course, the attenuation length, which is for muons literally extremely long, is not so long for neutrons, but is longer than, for example, for electromagnetic particles. Then the interactional information is lost. And of course, things can arrive very, very late. Now let's look at the simulations. So I'm actually, if you look at the paper, there are very dense plots, and I just I just made the basic lines I left, and everything else I deleted. The details you can see in the paper. But if you have a photon shower and plot the muon energy spectrum here, it's a black line. It's a photon shower of 5 times 10 to 16 electron volts, sea level. You observe the muons. Then here you see it for protons, and here you see it for iron primaries, same energy. That's what we expect. It's a 40% increase, and we understand this part. It's only as a reference for you. If you do it with neutrons, you have to enhance your skill all the way down to very low energy. And you see the same part, the high energy part is this one. This is where the neutrons are basically pair produced. And you see, interestingly, the black is the photon. Yeah. And then you see the proton purely electromagnetically produced neutrons is a dashed one, or the blue is dashed is purely electromagnetically produced neutrons for iron, and they're all on top, as they should be. But we get the hadronic contribution for the hadronic showers, and that is, of course, absolutely dominant in this range. So you see here this part that is equivalent to the muons. Then you see the resonance part that's coming from the resonance cross sections in air. Then you see a thermal part, basically. Oh no, not it's like a 1 over E distribution. That's elastic scattering of the neutrons propagating as a cloud. And then you see the backscattering on the surface. That's the thermal part here. Interestingly, if you look at this here in this range, the photons are on par with the hadrons. There's no real difference. So it's the same number of neutrons at low energy as you from a photon shower as a hadron shower. So it's a big difference, actually. Now, if you look at what it's changing if you go to different depths. So we look at now at one energy, we look at different depths in the atmosphere. And you know, muons are literally not absorbed. So you see that the muon lines are all on top of each other, except for the low energy end where the muons start to decay. If you go to the neutrons, it's of course different. So high energy at the high altitudes, you have more neutrons, and the number goes down all the way. But you see in air, you get the neutrons going down here. Once you reach the soil, the ground, you get them backscattered, and you get this enhancement of thermal neutrons depending on how humid, well, let's say how much water or any light elements you have in the soil. Absorption lengths you can calculate numerically from the simulation, and you get between 80 and 200 grams, depending on what energy you are. Like you have more of an absorption here and less here. Now, if you look at the energy dependence, and that's a little bit a dense plot. So we scale 10 to the 16 with 1, 15 times 10, 14 times 100. If it's scaling linearly with energy, all three lines would be on top. But it turns out that the high energy line is actually, you see the high energy line is the lowest one, and the low energy line is the highest one. And that's because it's scaling with the power for a hadronic shower 0.9. You know, it's if you scale to 0.9, but you do it with a scaling of 1, you invert this order. And if you look at the photon-induced ones from muons, they scale nearly perfectly with the energy of the primary photon, as we would expect. Yeah? This is why, because photons have to produce muons, and it's 1-to-1. So we understand this part. If we now go to the neutrons, you see that the hadronic part is more or less on top of each other. You can't resolve it. But then you have the situation that is opposite. The black line is here the lowest one. The black line is here the highest one. You see actually the photonic part, the photodissociation of target nuclei, that scales linearly with energy. Therefore, you get this one here higher than the other one. And you see it very nicely pronounced for photon-induced showers, where you have just photons and very few hadronic interactions. And then you see that this scales actually linearly with energy. If you look then at the longitudinal profiles, it's, well, probably actually takes a lot of time to look at those plots. So this is now many more energies, all scaled like from 10 to the 18 all the way to 10 to the 14. And if you have photon-induced showers, you see that the neutrons at maximum are literally scaling with energy as we would expect. And then you have the absorption, and therefore you get at ground a net effect of this way. For muons, there's little, oh, excuse me, this is of course for muon, this plot is all for muons, yeah? So it's for muons, we expect that the muons scale with energy, and then this is what the muons really, the attenuation in the atmosphere is. And the same is here for the hadronic shower, except that the scaling is 0.9, and therefore you see it this way. For the neutrons, if you compare the neutrons in photon-produced showers, it's very similar to this one, you see, except that it's a little bit, the peak is earlier in the atmosphere and more absorption. And if you look then at the neutrons for hadronic showers, you get this very strange situation that there is an interplay. At maximum, you clearly see the difference, but at ground, you wouldn't see it. It looks like scaling with energy, although it does not scale 1-to-1 perfectly with energy. It actually scales with 0.95, whereas this one scales with 0.9. So that's really making a difference. But the key is now, if you look at the time, So this is the muons, the energy distribution of the muons resolved into different time slices. So this is the early time slice. This is essentially below a nanosecond, the early arriving muons, the late arriving muons. So this is, think of it, the latest muons are, well, you know, our last spin goes up to 10 microseconds, but it's actually, the bulk is somewhere here. It's in the nanosecond range. If you go to the neutrons, we go actually to the millisecond range here. All the way, the late neutrons arrive very, very late here. And you can resolve all the structure. You see, if you go to the early times, you see the hadronic part. If you go to the late times, you see all the multiply scattered neutrons, and you see it's actually really very nice, and you can distinguish the different types of interaction processes. Now, how does it compare if you had a detector that had the same sensitivity of neutrons, to neutrons and to muons, which of course you don't have, but let's assume. That's the plot that is shown here. You see this is a curve of the muons, the black line here, and the muons then, let's say, go up to 1 microsecond only after the shower front is a gray line. And if you go to the neutrons, you see the blue. And if you go to the neutrons from 1 microsecond to 20 microseconds, it's a red one. And it's essentially the same number. It's a very interesting story. This is for 400 meters. Yeah, it's for 400 meters from the shower core, and it's wow, it's almost South Pole altitude. It's high up. And you can go, of course, go deeper at 1,000 grams sea level when the muons are going to win, because attenuation is they are less attenuated than the neutrons, but it's not much of a difference. And so it's actually an interesting channel, except one of the problems is it's very hard to simulate. Secondly, it's very hard to measure those neutrons. And that brings me already to the end. And what I want to show you here is that neutrons are actually very interesting subluminal particles. They are very abundant in air showers. And they are, of course, difficult to detect because neutron detectors typically are very slow. And so not easy to use in air showers, except if you have scintillators and look for late pulses, they are there. Now, what is a percentage? And that is a rough estimate because we don't have really the proper scintillator material, and that's up to the different collaborations to work on. If you have different neutron energies, and we really talk about the bulk of neutrons is in this range, 10, 20 MeV and up. And so we live for the scintillators at a level of percentage range to see them. So you have to multiply them maybe by 1/5 or something. In the water Cherenkov, it's literally impossible to see them. It's a very, very small effect, even if you put the threshold very low. And so I think actually it's a channel we haven't explored, but we have a lot of modern experiments that can do it. And we can do a lot of interesting physics with it. Thank you.
Very nice talk, Ralph. I just wanted to make a comment that we had worked on Grapes 3 scintillator. We had developed and had reached fairly low sensitivity. We could see radon decay products down to 300 keV. And then we were running the detector with multi-hit TDC. And we could see a whole spectrum of delayed particles, from 50 nanoseconds onwards, not just microsecond, a few hundred, 50, 100 nanoseconds onwards up to microseconds. So neutrons are there.
Yeah.
We didn't make use of it. And I really don't know how we can use it, but the signal is there. So I'm very happy to see your details.
It's definitely difficult to use them, but nowadays we have the tools. We could do it. Yeah.
Yes.
More questions?
Yeah, very interesting indeed. I mean, you showed the possible contamination of the scintillators by late neutrons. So if you in one of the exactly there on the other slide, I mean, where you showed the trace, for example.
Oh yeah, okay, yeah. No,
yeah, here. So actually, then you would at some point decide to truncate the signals, right? I mean, for the analysis. I mean, because
Yeah.
there could be contamination then by neutrons, the probability increases and the later you are with respect to the main signal.
So in Auger, what David Schmidt showed in Auger, this would be the standard integration time window
Yeah.
driven by the water Cherenkov tank. And
Yeah.
if we apply to the scintillators, of course, you don't see the neutrons.
Uh,
Yeah, it's that's a way you can deal with it, but
Mhm.
it's a matter of deciding whether you want to have that
yeah,
or
yeah,
not.
no,
Yeah,
sure.
so
I mean,
and
right.
but the interesting part related to it is, of course, here is Hajo Drescher and Glenys Farrar. They conjectured at the time in 2005 that this is the reason why Agaza saw those excessively high energy events beyond the GZK cutoff, because they had this logarithmic amplifier where you are very sensitive to this part. But at the time when they did the study, they didn't really have such reliable tools to do the simulation. So it could be related to it. We don't know.
Yeah,
It's still an
exactly,
open question.
Now, since that slide enough, may I ask, I mean, this fluence which you showed in
Yeah.
on that slide,
Oh yeah, this one. Yeah.
newtons per square centimeter.
Yeah.
So that is at a certain distance, right? I mean,
Yes. Yeah, I've not copied this part out of the paper. Yeah.
okay,
So,
okay.
but it's large, you know. This is high altitude, small distance, but it's
You know, you referred to the work of Yuri Stenkin.
Exactly.
So I remember interacting with Yuri, and he had developed a scintillator, which is basically you can roll it like a sheet of paper, and where he deposits a compound of with lithium-6.
Mm.
And his claim was that he, for every neutron, capture, he gets about 50,000 photons, and he was looking for opportunities to install that detector. So if you are interested, but I don't know, he being a Russian, so there may be other complications.
Yeah, that
But
might
it's
be.
a very impressive detector.
But the real problem is, like, Auger has 1,600 detectors, so he would have to have a lot of sheets. Yeah. So it's yeah. No, but
Item,
yeah.
yeah. I think it's probably all. Thanks, Ralph,
Yeah.
again.